Section 7.2 talks about the calculus of parametric equations or parametric curves. So recall, a parametric curve is the same as a rectangular curve with the exception of direction. And domain applies on the values of f of t or y of t. In our case, I'm going to call them x of t and y of t. Now consider a plane curve defined by the following parametric equation. Suppose that x prime, which is dx dt, and y prime, which is dy dt, exist. And assume that x prime of t doesn't equal 0. Then the derivative dy dx, well, let's see how this works. We have x equaling a function of time, y equaling a function of time. So if I decided to look for dy dx, well, by the chain rule, y depend on t and t depend on x. That's how the chain rule worked. Well, dx dt, instead of multiplying, I could divide by the reciprocal. Oh, I wrote that wrong. I apologize. That's dy dt. And that will become dx dt. Or simply put, if I want to find dy dx, y depend on t and x depend on t, whatever makes it simpler to remember. So it's fairly simple. We have derivative of parametric equations, and later on derivative of polar functions. That's a bit more complicated, but we'll talk about it when we get there. Luckily, that's not in this class. And here we are. Now, the first derivative is really straightforward. It's right there. The second derivative is a bit of a trick. I used to derive it back in the days, but I'm not going to do that anymore. If I want to take the second derivative with respect to x, that would be take the derivative with respect to t of dy dt divided by dx dt. So this I will provide on your test. You really don't need to memorize the second derivative, but you just have to use it. And I'll do a couple of examples out of that, and I'll show you how that works when we get there. I thought I got it. Okay, we'll see. All right, well, let's start with the first examples, couple of examples. For the following exercises, each set of parametric equations represent a line. Okay, here we're talking about lines. Without eliminating the parameter, find the slope of each line. Well, the slope is dy dx. Y is a function of t, and x is a function of t. So that's the simplest way you could remember that. Let's go vertically. So y depend on t and x depend on t. And the derivative of y with respect to x is -1. The derivative of the derivative of y with respect to t is -1. The derivative of x with respect to t is -1. And my answer would be -1. And I don't need to remind you of what kind of applications that derivative holds. The same deal here, dy dx. Well, y depends on t, so you could read. I'm going to write it again just this time. Y depend on t and x depend on t. That turns out to be a 6 over a -3, which is -2. Of course, if you solve for t and substitute that in, you will get the same answer, but that's a lot of work. It's much more efficient this way, and that's going to alter certain formulas that we spent a long time trying to derive to become special cases. And here we are. For the following exercise, determine the slope of the tangent line. The slope of the tangent line. Then find an equation of a tangent line at the given value. Well, at pi over 4, sine is 1 over radical 2 or radical 2 over 2. And cosine is 1 over radical 2 or radical 2 over 2. So my equation is y minus y1 equals m into x minus x1. And this is point slope form of a line. What's missing? The slope dy dt. And here I'm going to go straight for it. Derivative of y is -3 the sine of t. Derivative of x is 3 the cosine of t. And I'm aware what that is. That's negative tangent of t evaluated at pi over 4 dy dx. I'm sorry, I keep on writing dy dt, my mistake. Dy dx happened to be a -1. So there's my answer. Same deal with this problem. At t equal -1, my point is -2, -1, y minus y1 equal m into x minus x1. Of course, if you'd like to solve for y and write the equation in point slope form, you are welcome to. It doesn't really matter. An equation of a line is an equation of a line. So I need to find dy dx. Well, we know what that is. Derivative of y, that is 3t squared. Derivative of x with respect to t is a 2, evaluated at t equal -1. That is positive, that's 3/2. And there it is. Again, you want to solve, you can. There's my answer. Now, parametric equations hold a lot of very special applications. 78 for x equal the sine of 2t, y equal the cosine of t, and t varies between 0 and 2 pi, not including 2 pi. Now there's an issue with the domain. Find all values of f at which the horizontal tangent line exists. The horizontal tangent line exists. Well, if you recall from back in the days, horizontal line means the slope of that line equals 0. When they say the horizontal tangent line, that means the slope of the tangent equals 0. Well, slope of the tangent is another name for a derivative. The derivative of y with respect, that's twice the cosine of t. That is cosine of 2t times 2. And this exists when 2 cosine of 2t doesn't equal 0. Well, let's see how that works. Cosine of 2t doesn't equal 0. The reference angle is cosine equals 0 at pi over 2 and 3 pi over 2. So that is pi over 2 plus pi over 2 plus pi k, where k is all integers. What equals that? The angle. What's the angle? The angle is 2t. This is trig. Multiply by a half. As long as t does not equal pi over 4 plus pi over 2k, the slope of the tangent exists. Now, an application of those normally, again, I know we're not going to go over the application, but I'm so tempted. I've seen one application of it where you have the slope of the tangent equals 0 at multiple values of t. Those are not functions. And that happens at these values. And the slope of the tangent does not exist at values of t. Each value of t gives you a point. One of the applications that I used back in the days were the DNA structure. Of course, there are many other applications, tracing rotation around of satellite around the planet you know, all of these things. But we're not going to worry about that part. We're just going to worry about, all right, well, how are we going to use this to our advantage? And the use is not really in the first half. Mainly, it's in the second half. It's right there. Now, a practice. Find the second derivative of this. Well, dy dx is kind of straightforward. Derivative of y with respect to t. So I'm going to write that down. Dy dt over dx dt. That is 1 minus 2t. And that is 4t cubed. That's the first derivative. The second derivative, again, I used to derive it until they figured, well, there's not much. They really don't ask for any applications, really. The second derivative with respect to y is, and notice how this works. The derivative of this divided by, now be careful, dx dt is this value, yes, but if it's not simplified. So I could just copy the denominator and say the denominator is 4t cubed, or simply take the derivative of this again. But the top, I'm going to take a derivative with respect to t of this. That means I have to apply the quotient rule unless I split that up. Unless I say, look, that is 1 over 4t to the negative 3 minus 1/2 t to the negative 2. And the derivative of that would be negative 3/4 t to the negative 4 plus the 2's cancel out. So that is t to the negative 3. And there's nothing wrong with you leaving it like that. If you want to clean it up, that is negative 3 over 4t to the 4th. Now, for the homework, you should clean it up to match it with the back of the book. The LCD is 4t to the 4th. This is missing a 4t top and bottom. And this is missing a 4t to the 4th top and bottom. So the answer is really negative 3 plus 4t divided by 4 times 3, 12t to the 7th. And if you were to use the quotient rule, you would have done the same thing after you simplify. Anything I box is a fair game on the test. So on the test, I just want to see the calculus. I'm not worried much about the algebra. It comes up later on anyways. Now, let's talk about another use of this that's going to make our life really simple. Do you recall back in the days when I derived the curves, when we talked about L equal the integral of ds? That was either 1 plus f prime of x squared dx, or that was 1 plus g prime of y squared dy. If you recall that from back in the days, well, here, guess what? Since x is a function of time and y is a function of time, then L, we call it S in this book, S, which is L, the length of a curve from A to B, that happens to be the integral from t1 to t2 of the square root of dx dt squared plus y prime squared dt. Fairly simple. Now that would be something like section 2.4, right there. Remember when we derived this? The same analogy, but instead of using dividing by dx, I would have divided by dt everything, right? If I was to divide this by, here, let me use that laser pointer. Divide this by dt squared, dt squared, dt squared. That will be the s dt squared. That will be the x dt squared. That will be the y dt squared. And if I square root both sides, I'll get that. And if I multiply by dt, I'm looking at the x dt squared, dy dt squared, dt. And the beauty of it is this confusing part when we did the rotation, if you recall, this here is fairly simple. Why? Because I don't have to choose anymore. This is already in terms of t, and y already is a function of t, so it works out perfect. A function of t, a function of t. So I don't have to figure out which direction I want to take this with respect to y or with respect to x, because it makes no difference. They work out the same way anyways. So here, let's talk about this again. If I wanted to find the arc length, L equal the integral of ds, that is the integral from 0 to 2, no need to worry about that, square root of dx dt squared plus dy dt squared with respect to t. And we could work that out with ease, right? I'm assuming the work for you, that's simple, that's just a constant, so you end up getting, what is that, 16? That you end up getting 5 times t evaluated from 0 to 2, so you get 10. And if I look at the next problem, the same analogy applies. You say, look, L or S, whatever they call it, that is the integral from ds, that is the integral from 0 to pi over 2 square root of dx dt squared, that is negative twice the sine of 2t squared plus derivative of y, that is twice the cosine of 2t squared dt. And this is the integral from 0 to pi over 2 square root, that is 4 sine squared of 2t plus 4 cosine squared of 2t. Factor the 4 out, and the sine squared of 2t plus the cosine squared of 2t happen to be a 1, and you go from there. Fairly simple integral. Again, that's 2 times t evaluated from 0 to pi over 2, so that is 2 times pi over 2 minus 0. That's simply pi. I keep on saying completed and I get excited and I finish it anyways. It's all good. Now, what if we're talking about rotation? Find the area of the surface rotated about the x-axis. Surface area is the integral of 2 pi with respect to the x, y ds, if you recall. In this case, fairly simple. 0 to pi over 2. 2 pi is a constant, you could drag that up front. Y is right there. That is a the sine cubed of theta. Again, they use theta, they should use t to separate between polar and parametric. ds is dx dt, 3 negative 3, no, 3a the cosine squared of theta times negative the sine of theta all squared, and derivative of this, bring the power down, 3a the cosine squared of theta times derivative of sine, which is cosine of theta squared d theta, or I'd rather you switch everything to t. Again, not a big deal. So that's the integral 0 to pi over 2. 2 pi is a constant, a is a constant, sine cubed of theta square root of 9a squared cosine to the 4th of theta sine squared of theta plus 9a squared cosine to the 4th of theta. I must have messed up somewhere. There should be a, oh, bring the power down, subtract 1 from the power. Bring the power down, subtract 1 from the power, that's still a sine. There you go. So the sine to the 4th. So that is 2 pi, the integral is 0 to pi over 2 sine cubed of theta. I could factor out of both of those 9a squared. I could factor cosine squared of theta, sine squared of theta. I would be left with cosine squared of theta plus sine squared of theta. And that's the most famous identity of them all. That's a 1. So basically, the radical clears out. I'm looking at 2 pi, the integral 0 to pi over 2 sine cubed of theta times 3a the cosine of theta sine of theta d theta. Altogether, I'm looking at 2 pi, the integral 0 to pi over 2. There was an a, wasn't there? Now I'm going to take the 3a out. That's going to make this 6 pi a squared. And we're dealing with the sine to the fourth of theta cosine of theta d theta. Let u equal sine du will be cosine of theta d theta. Remember the rules. This is 6 pi a squared, the integral of u to the fourth du. Now if I put 0 in, I get 0. If I put pi over 2n, I'll get 1, and there it is. That is 6 pi a squared times u to the 5 over 5 evaluated from 0 to 1. That's 1/5. So that's 6/5 pi a squared. Set up, do not solve on a test. That's all you have to do. Just saying. And I want to do one problem. Of course, I want to do one of each. This section is not that challenging, really. If I rotate above the y-axis, the surface will be the integral of 2 pi x ds. Well, here it's going to be the integral 0 to 5 automatically because everything is in terms of t. 2 pi x is really 3t squared, square root of dx dt, that is 6t squared, plus dy dt, that is 6t squared squared dt. And from there you could continue on. Let me just get you started really quick. That's 36t squared, that is 36t to the fourth. Factor 36t squared out, that'll be 1 plus t squared dt. You could take this out and proceed, whatever that is. Set up, do not solve. This is all I want on a test. And that pretty much concludes this section.